Hello, and welcome to Advanced Number Theory. It's me, your boy, the Lumber Snack, your host on this mathematical journey that we're about to go down today. And here is the thing about numbers is it's how we account for things. The numbers that we've created are nothing more than just symbols that have, stood the test of time, constants that have been part of our mutual shared reality, and they behave the way that they do because that's how they behave. And so what are we looking at here? Well, I think what science and mathematics has tried to do for millennia so far has been to isolate the monad variable. The monad variable. This thing right here. This kind of like perpetual circular thing. That's right here. That's right here. So we've been trying to figure this out because for whatever reason, this process of 3 behaves with concepts of 4 numbers, those 4 numbers being 5, 2, 7, and 9 as the core sequence. And so it's okay, what do we need to account for versus what has already been accounted for, Because we use the decimal system. We use decimal base 10 notation, and what that means is that within the specified range of 10 numbers, you have 9 symbols that make up the representation. And you see here, you have the first 8, and then all the way down to 32 right here. Believe it or not, the numbers actually go bigger than 32 by a little bit. And, those numbers are already accounted for on this thing right here. This thing right here called the Fibonacci sequence. And so these numbers, what's nice about these concepts, this kind of thing right here, is that all of these constants, all of these number theory, whatever you want to call them, they have already been accounted for. They have been accounted for as theories, as concepts, without the need of the decimal base 10 system. The only reason we're able to see them as they are like this is because of the decimal base 10 system. And then it says, okay, so what all do we need to account for? So what we have accounted for right now is we have the 1 accounted for, the start point. We have the 2, the 3, the 5, and the 8 that we have without the specified need of, the decimal system. And then we also have these that you don't really need to account for. You've got 13, 21, 34, 35, 89, and 144. These number concepts have been accounted for because they're on the Fibonacci sequence, and thus, because 144 is accounted for, that's 12 squared, we have the range and the specified numbers that we have at our disposal for conceptual theories being a range of about 1 to 12 is kind of the way the math checks out on it. And then, so you think, okay, what are some other things that we need to take into account? So we have the 3, but we don't have the 7, but we have 3 times 7 right here in the middle. And I've put it on a pedestal because 21 kind of behaves as a number that is put on a pedestal, because we have this 144 because it's the 12 is a reflection of 21. It's mirrored. And so it's not put on a pedestal per se. I just accidentally wrote 34 instead of 21 and then had to scratch out the 21 or 34 because you need 2 and 1 to get 3 and 4 is how the simple math checks out. And so you say, okay, so Gottfried Leibniz, the guy who discovered calculus independently of Sir Isaac Newton, he developed this system called binary, which is used in computers. It's used in machine learning. Basically, it's a way that we can simulate our experience, our real, universal concepts of numbers. We can harness it and take advantage in the realm of computers and mathematics. Because if that wasn't possible, you wouldn't be able to watch this video right now. You wouldn't be able to talk on your cell phone. You wouldn't be able to drive that piece of heavy equipment. And so, because we're looking at ranges, in numbers, we think, okay, with binary, what Gottfried Leibniz has done is he has completely removed the 5 to create that one element. He's completely removed the 5 from binary. And so all that you have left is 2. And when we're looking at the Fibonacci sequence, we see this range of up to 8 numbers before you break past any sort of hypothetical decimal point, And so for binary, for this exercise, for what we're doing, what we're looking for, what we're trying to prove, is we're going to list these in 8 ranges. We're going to list these in 8 ranges, or ranges of 8, yeah, because we have 8 right there. 8's the final product of this kind of range right here, that all 3, 2, 3, and 5 are all accounted for. And so then we also think, okay, so what are we doing with this? Why are we separating the binary numbers, and why are we looking at the binary numbers? Because they're kind of like the inner workings. Like, you took an X-ray of the numbers, and now you're left with just the bare bones, just the base sequencing of 1s and 0s that get left because of this conceptual monad that exists. Because we're using this is an expression of the duad, but you've got that expression of the monad that's still in being investigated. And so if you don't know how to write binary, I'll tell you real quick. Basically, it's only 1s and 0s. Anytime you hit 1, a 1 becomes a 0, and the 1 gets pushed forward. So you go 1, 10, 11, 100, 101, 110, 111, and 1000. And so that's the range, and you get at this 8 point, you get 4 digits. You get expressed 4 digits. And then it's like, okay, well, below that at 16, 8 times 2, 4 squared, 2 to the power of 4. At 16, we get a range of 5 digits instead. And so that's kind of where real numbers, like big numbers, really start to take shape. Because up until this point, we're still bound by that base 4-digit sequence that somehow accounts for 8 and accounts for 15, And then after 16, we've got 5. And we've got that routine, even right here, if we're looking at different integers, we've got 1, 2, 3, 5, 8. That's 5 different integers. The 1 is there twice. Which you also see that 1 there twice at this point of 3. You also see it at that point of 3. But hold on, you also see that 3, 7 point at this. Not to mention, you have this area right here where 5 is, where there's this empty hole directly in the middle that is yet to be accounted for. And you see this point that hasn't been accounted for, multiple places. For example, you see it right here with 9. You have those 2 missing. Well, that one's easy, because those 2 ones right there that are part of the 3 that this system accounts for, those probably go right there. And it's like, okay, so what about that? 7's pretty close, but we need to find an counting thing for that. And so you kind of get something right here where those 2 1s fit into the place of that 0. And then you get to 17, and it just keeps going. And then you get to something like 21, and you've got 5, 5 on either side, but it's not perfectly accounted for because there's that middle, 1. And then 24 accounts to the 12 concept, because 24 and 12 are pretty similar ideally. And then you also get 27, where you get, all right, you're kind of closer to this 5 principle, because now you've got 2 1s on either side. So you've got that 2 on the other side from 3 because 27 is 3 cubed. And so we're just going to go through and fill in the rest of these real quick. 28 is 1, 1, 1, 0, 0 because, 28 is 7 times 4. And so now we get this area accounted for by the 4, and we get this area accounted for by the 7. You see how that kind of works. And then we go 1, 1, 1, 0, 1 because we have to uptick. And now we've got another prime number. So this is something that becomes difficult to account for using exclusively binary and those 2-digit sequences. You need something more to account for that. And we're going to keep going, 1, 1, 1. And then it's like, okay, so we've got 4 1s and a 0 right here because that's 15 times 2. So we've got that kind of figured out. And then we've got 5 1s right here at 31. Similarly to how at 7 we have 3 1s. We've got 5 1s before we get to 32, which has an expressed range of 6 digits. And now binary moves forward in 6 digits until you get to 64, and then it'll be 7 digits, so on and so forth to infinity. Because that is the beauty of binary. But, we have stripped down these numbers to their bare bones. We've basically taken an X-ray of these numbers, and it goes, okay, so we've taken an X-ray. Well, how would we go about getting a better picture of these? And so we go back to this concept of 2. And we think to ourselves, how is 2 represented? What is the way that 2 kind of represents itself in the real world? And look at that. And you go, okay, so I know that 2 plus 2 equals 4. But also 2, when you merge it together with itself, becomes 4. So you've got 2 different ways to get 4 using exclusively the one number that is 2. And so knowing that we can strip the 5 completely out of this, to just leave the bare bones of the 2 concept, what if we introduce that 5 back in? Then what do we take out of the number sequence? We've gotten it back into decimal at this point. We've gotten these numbers back to where they are. How do we break it down further? How do we account for this right here? How do we account for this 3 right here? And so you use quaternary. You use quaternary to account for that 3 because even though quaternary is 4, you get the digits 0, 1, 2, 3 right here. And they kind of go in this order. You got 0, 1, 2, 3. And that's because if you take 5 as the midpoint, 2 is 3 less than 5. So that's going downwards. So that's where you get right here. 7 is 2 more than 5, which is why you get the forward expression. And then when you're using the digital root, anything that you add to, anything that you add to 9, the digital root remains the same. And so if you add 7 to 9, you get 16, which we'll add right here, which in 16 you get 4 squared. And so that's really where you get quaternary, is in this branch of 5 numbers, because 5, this 101 range, is expressed right here. You see it? You following? You picking up what the lumber snack is putting down? Because it's fresh and tastes like chili powder. But how are we going to now convert these numbers to quaternary? Well, it's easy, because it's the exact same way that we accounted for, or we got to binary. So the only difference is, instead of going, from 1, which 1 is always 1. That's the one thing that we've been able to agree on, that the monad kind of, it's just, what is this 1? What is this 1 that's so versatile and so necessary to everything? And so when you go into quaternary, now you account for 2. You account for 2 because 2 is part of it. And then you also, because you account for both 1 and 2, you've now accounted for 3. And then where do you go from there? Where do you go from there? Well, you go to 10. And so this 100 gets broken down to 10. And so why is that? Why is that? Why do we do that? Because the way I see it, 2 is only a thing because you need to account for that fourth concept. Because you need to account that there is 3 things outside of the original point, which, it'll go with a lot of philosophy. Because you have these 3 things with this original thing. And then this original thing, the line gets blurred between 5 and 9 because of these 2 things. And so it's kind of like trying to figure out, how to get down to it. And then you get 110 because 4 is not a triangle number, but 10 is a triangle number because of 4. And 10 is the third pyramid number or tetraangular number or whatever because 4. So that makes sense. We're going to keep going. We're going to just see how the numbers present themselves. Okay, and then so at 5, you get 1, 1. Well, hey, look at that. This binary representation up here, this 1, 0, 1, has now condensed in the same way that 3 has been condensed in the binary. So, okay, we've figured out there's a constant between that. And the constant is this kind of binding agent between them, There's a weird binding agent between them, and so, but the important thing is that we've accounted for this. We've accounted for it. Which is why, this is one of the big reasons why it leads me to believe that 5 is the origin of all number concepts, is because of the way that it behaves. And so we look at this and we see, okay, so these 2 1, 1 constants, they are actually right here. They're actually right here. So you need the 3 to get there. You need the 5 to get there. But because of the way base, notation works, it's just expressed as 1 and 1 make 2. If that makes sense. And so we'll continue. We have 12 right here, which tracks because 6 times 2 is 12. And so using that quaternary and that concept of 4, you are able to achieve 12. And then we've got 13. And now we say, hold up. You're telling me that this 3 constant, this concept, this symbol that we use, is not specifically ordained for this concept? And why is that? Because 7 is not a multiple of 3. The way that you get 7 is because 3 plus 4 equals 7. And when we look at it critically, we know that this 1 right here, this 1, is actually a 4. Because we're using quaternary instead. And so this becomes 1 plus 3 equals 4, but 4 plus 3 equals 7 for the same fact. And then over here, we get 2, 0. And so it's like, okay, now we've got that concept of 20 figured out. We've got that concept of 20 figured out. We figured out that we've got a concept of 10 here, and that 10 is represented by 5 times 2. But right here, it shows clearly that there's a bridge where one is less than the other. And so we get 10 right here, we get 10 times 2 right here, and that's 10, 10. And so we look over here, and we're like, okay, cool. So 2 times 10, that gets a representation within the 8. I'm hoping you're following, because this is, advanced number theory. And so we just keep going along, and we get to right here, and we say 21. And we say, hold up. So we were expecting that this 1, 1 is in the middle. But what it actually looks more like is that this 21 gets represented right there in the heart of this, right there in the core. So this 10 and this reflected bit comes together and forms 21, which, 21 is accounted for in the Fibonacci sequence. So we know that that kind of gets accounted for using this quaternary form of expression. Not only that, 21 is 7 times 3, and you can draw on whatever you want to. Then we have 22, and we see, okay, cool, so where in binary, 3 was the 1, 1, and then the next kind of repeating number like that was 7 at 1, 1, 1, 3 ones. Now instead we have concepts repeating as far as similar symbols being added to each other. And we get that at 5, and we get that at 10. And so logically we know 5 times 1 is 5. And then we also know 5 times 10, 5 times 2 is 10. And so if 5 times 1 is 11, and 10 times 2 is 22, then we can think and say, okay, cool, so what's 5 times 3? And then we can more or less confidently put down that we think it's going to be at, 5 times 3. That's going to make sense. And if we look at the binary representation, it's 4 ones, which gets broken down into 2 3s, because that's where we see these 2 ones, is that we see this is 3, this is 3, and this is 3. And then in quaternary, we see 3 and 3. So it's a more simplified and fanned out. But we need to go and make sure that we're correct. And so we're going to continue using the quaternary representation. And so we see 23 at 11. And we think, okay, cool. So this 3 constant right here is different than this 3 constant entirely. This 3 constant is used to explain numbers that can't be properly explained, because what we see so far with numbers that have 3 as the ending is typically that they're primes, because 7's a prime and 11's a prime. However, that gets thrown out at 15. However, that is predominantly because we have the equal 3's. We have the equal representation inside the number 15. And so we're just going to continue, and now we're at 30. And we say, okay, cool. So looking at binary and looking at quaternary, we see that this 1100 is actually 30, because this 11 breaks down to 3 when you expand it just a little bit. And then we're just going to keep going. We have 31, which is exciting because 13 reflects itself in quaternary. The other place that we see this is in base decimal notation, because 12 and 21 reflect themselves, And so we keep going, and we see 32 right here, because this is 7 times 2. And if 11 is 23 and 14 is 32, there's 3 between them. So we see the numbers coming up to the numbers going back down, kind of a equal give and take. And then we can see that we were correct and spot on with our assessment that 15 would be 33. And then at 16, we, instead of getting 5 digits, we get 3 digits at our devices. And so we see that this is mirrored from, the 4 to the 16, because 4 is the square root of 16. Where we removed 1 0 1 0, we removed 2 0 2 zeros, and it's basically the same thing. And so what we do is we continue. Okay, so we got 1 0 1, and so we are still missing the accounting for this 17 constant, this number right here. We're missing this number. This number is difficult to find. And so we know that we're missing because this is shadowed in here. And we know that it's going to be difficult for us to take anything else out of the decimal number system, because we can't. Because the decimal number system is only a sequence of 4 numbers followed by a 5th binding agent, as dictated by the theory of the monad that is foundational to mathematics as a whole. And so we're still missing this 17, to the point where we were missing something with this 5, We're now missing that same similar constant with the 17. But we're going to keep going. 102, because 12, and this is 9 times 2, and so that 21 times 2, and you get 102 as the 2 splits that way and the 1 splits that way, creating the gap that is this 0 between. And then at 27, or this is 19, we have 103, and so we get a similar range for this 7, where now there's a 0 between the 1 and the 3, and we know that this is prime because it's 19. I don't want to explain that one further. That one's kind of just like, you can't multiply to it. And then we get to 20, which is 11 and 0, similarly to how 6 was 11 to 0 in binary. And then that becomes 12. And then this is 101, 0, 0, so we've got the 5 out front and 2 zeros behind, and now we've got 11 and 0. And then at 21, we get 3 1s, which is a direct match to 7's binary representation. It's a direct match to 7's binary representation, which is also a direct match to 9's quaternary representation. And we find it all circulated at this 21 spot, this kind of magic variable that also exists right here, you know. It exists right here. And so we're just going to continue going on. 22 is 112, 11 times 2. 23 is 113 because of the prime constant. And then we've got 120. Similarly to how 12 is 11 and 0, we see right here 6 and 24 is 6 times 4. And so you put the 12, the 1, 2 right here on the end, and you round it up to the 0. And that's how quaternary works. And then we just keep going because I like this stuff. And then this is an interesting one because in quaternary, we see 121 at the quaternary location at 25. And it's, okay, so why is that important? Well, it's because 11 is right here. And 5 is right here. And what's 5 squared? 25. And what's 11 squared? 121. So now we start seeing where the process for compounding mathematics begins. And we can see definitively that this conceptual 11 is actually based in the number 5 because of the binary sequence, because we're removing, when we're converting to binary, we're removing this 5 out of it entirely, which is why we have that gap right here. But when we reintroduce the 5 element to get quaternary, you know, we find that 5 element right there in 11. Not only that, when you add these two numbers together, you get 5 for the 11. And then you get 5 squared and 11 squared. And so that is one of the big explanations for why we compound numbers. Not going to learn that in college because I don't think anyone's discovered that yet, besides me. And then we're going to continue. 26 is 13 times 2, so we got 31 times 2. Doesn't really work. But when we get to 27, no. This is where we get the actual foundations for our decimal 10 system in mathematics, is in 3 cubed. 9 times 3. 3 cubed. And so, yeah, you get it there because you get 1, 2, 3 for its quaternary representation, 11, 11, 0 in the middle, mirroring, you know, what 5's binary representation looks like in this 27, and 27 is 9 squared. So, and you get 1, 2, 3. And then at 28, you get 13, 0 because 7 times 4 is 13. 1, 3, 1 because that 9 constant's there, and that 9 constant is opposite, you know, that constant of 10. Because I think philosophically, we're always trying to get between numbers. We're trying to figure out, you know, what really exists in that gap between them outside of just standard decimal. which the reason that we can use fractions and decimals is because of 7, because it's that representation of a fourth concept for our numbers. And then we're just going to keep going. 132 at 30, 133 at 31. And then so we've got the 5 ones, but now we've got 1 and 3, 3 because 31's prime. And then we've got 200 at 32. And so this is where we look and analyze and ask questions. And so the questions are, okay, so what about this 3? What about this 3? We know that in binary, when you strip the 5 from the binary, we're left with this constant being at the number 3. And then we can in turn use this for quaternary to put it right there, to re-establish that constant. And then from here, we get similarities with this because now we have access to that 1 and that 3. That's 7, where we get 3 1s for the binary. So we break the logic of binary with 7, and then coming down here, we have 1 and 3. You feel? And so you keep looking, and yeah. You get 9 and you get 21, and so whereas this kind of looks like 5, you find 21 in this place, and 21's there, and 21, when you put it on the quaternary, is 3 1s, similarly to how 7, because 7 times 3 is 21. And then because of 9, because 9 has this 21 just bare bones inside of it, past what 5 has, we get to 27, which looks similar, albeit advanced compared to 5. And it's in 27 that we get the building blocks for our decimal notation. And so the next question to answer is, how do we remove the 3 from 5? How do we remove the 3 from 5? We've removed the 5 from 2, and because of that, we can introduce 5 to the base sequence. However, how do we account for these two similar constants? And that'll be the next lesson in advanced number theories. And I want to thank you for watching if you watched the entire way through. Leave a comment if you've learned something. I have something that this is all leading up to. So what I'm trying to prove, or what I'm showing you that I'm proving, has already finally been proven. And I have all the proofs. I'm just, expressing in simple terms all of the logic and all of the systems that are used in action. So I would love it if you subscribed. Yay for math. I would love it if you left a comment saying what number similarity was shocking most for you. And thank you for watching. Have a great day.